All right, we were working in section 15.6 last time on surface integrals, so let's just kind of review where we were to get us back in that mindset. We had talked about finding this mass on this surface of, and this shape happens to be a dome. It doesn't always happen to be a dome, but this one was. And we had taken the definition, but then the theorem of how to find the surface area as a mass. We find the mass of that. And we actually did one where it was actually surface area as well, because the function itself was 1, basically. All right, so we had done this one. We had talked about the fact that changing things into polar or even spherical, depending on the situation of what's going on, is totally still appropriate. And in fact, we did an example of each one. So this one right here was done just in the normal Cartesian plane. The one previous was done in polar. And then this one was done in spherical, because we just want to be an equal opportunity, coordinate system people of the day. So this is where we ended, and I had given you the homework, but we aren't quite done with it, of course, to get to all of those problems just yet. Okay, let me get a couple more slides in here. Never know how many we're going to need. All right, that gives us a couple. All right, so we have just a couple of things left to do in this section. The first is a definition. So this is definition 6.2. It says the following: let f of x, y, z be a continuous vector field defined on an oriented surface S with unit normal vector n. The surface integral of f over S and this has another name that you may have heard before, or the flux of F over S, is given by this formula. So the double integral over the surface S of the dot product of the vector field F and the normal vector N. I think I'm going to write at least a few of these remarks down for you so that you actually put them into your notes, because I'm fully aware that if I don't write them, you won't, right? Yes. So let's write down a few of the remarks that I have about this. So since n is a unit vector, when we take this dot product of f and n, this gives us the component of f in the direction of n. some sort of conceptual ideas of what this is doing. F is actually, or can actually represent the velocity field for a fluid in motion. Which means then that F dot N corresponds to the component of velocity that moves the fluid across the surface. One thing to note, you're welcome to write this down, I'm not going to write it, but this value, when you do this dot product, can be positive or negative. And the reason that can happen is because when we're talking about a normal vector, the normal vector could go in either direction based on wherever you are, right? You can have, if you had a normal vector, for instance, pointing up, in the direction of the z-axis, it could be pointing upward on the z-axis or downward on the z-axis and still be a unit normal vector. So you actually do, in fact, get a positive or a negative. And since since this happens, this is why we need to make sure that we have an oriented surface. Okay, so that's going to depend on because of that will depend on whether we get the positive or the negative normal vector. So you're going to see that they're going to describe how the normal vector is oriented when we are looking at this. Okay. All right, so let me show you how this works. All right, so our example that we're going to work with has the following directions. Evaluate the flux integral. Which is the double integral over the region S, or surface S, of F dot N ds. And I keep switching back and forth between n having a hat and n having a vector. I guess it doesn't really matter, but the hat means vector, just a specific type since it's a unit vector. So, all right, here's our example number 4. F is going to be 0, 1, y. And our surface S is the portion of z, which is the negative square root of x squared plus y squared, inside x squared plus y squared equals 4. And then we're actually told that the normal vector is upward. They're going to tell you what direction the normal vector is for this to make sense. Okay, is everybody good so far? Excellent. All right, the first thing that we need to do is we need to find out what or we need to describe, write it down, what our function f of x, y, z is. So do you remember how to do that from last time? It has to do with this equation. We just need to move the z, or move the other direction. We need all of it on the same side. Technically speaking, I'm actually going to move the other part of it just so that I don't end up with everything negative. But this is going to give me z plus the square root of x squared plus y squared. Okay, we did that last time. Do you remember doing that?
I thought you were asking a way more complicated question.
Sorry. Very straightforward question for a start with, yeah. The next thing we need to do is we need to find the partials. We need to find f sub x and f sub y and f sub z. So f sub x with this function, f of x, y, z, is what? Right, x over the square root of x squared plus y squared. Of course, you're doing a chain rule when you're doing that. Right, James? F sub y is almost identical, right? But it has a y in the numerator instead. All right, so what about f sub z? It's 1, and technically speaking, it can be the 1 or a negative 1. I know this says 1, but I mean, we made the decision of moving everything the way we did to keep it all positive, didn't we? So why was that helpful? Well, it was helpful in terms of not having lots of negatives, just sort of practically speaking. But the reason that that actually worked out well for us is because this said that n was upward. Okay, so since n is upward, the normal vector is upward, we're going to be getting the positive value of that. So, all right. The next thing we need to know is we need to get the unit value of this. That is, we need to turn this into a unit vector. Magnitude. Magnitude is the word I want. Let's find the magnitude. So we need the magnitude of the vector that is, well, actually I'll write it down this way and then we can have less of it written. Fx, Fy, and Fz. So I need the magnitude of that vector that I just found the 3 components of above. So this is going to be the square root of each of those individually squared and summed together, right? So I'm going to have x squared over x squared plus y squared over x squared plus y squared plus 1. And what happens when I combine those and simplify? Yeah, I just have square root of 2, right? Is everybody good with that? Fantastic. All right, so my normal vector is going to be the same f of x, y, f sub x, f sub y, f sub z that I have, but normalized with the square root of 2, because that's actually the length of ours, right? So I'm going to divide each of the components by square root of 2. So instead of having f sub x, basically I'm going to have f sub x over square root of 2, or x over square root of 2, and then, how do I write this down? We'll write it like this. X squared plus y squared, because there's square root of 2 down there, and there is the square root of x squared plus y squared. I'll write the second component the same way. This is the square root of 2 times x squared plus y squared. And then we have 1 over the square root of 2. Oops. All right, notation ended. The other component that we're going to need is we're going to need ds. I mean, if you look back up here at the beginning, we now have f, we have n hat, and we have to find ds. So, oops. How do I find ds? This is something we did last time as well. Do you remember? Which looks an awful lot like what, James? Yeah, it's the same thing when we found the magnitude here, isn't it? It ends up being the same formula for finding magnitude. So this actually ends up just being the square root of 2 and then dA. So ds dA is square root of 2 in other words. So I'll solve that for ds. All right. So let me write down what we're looking for and what we have so far. So we're looking for the double integral over S of f dot product with n ds. And we have the vector f. It was given to us originally as 0, 1, y. And we have the vector n that we just created on the previous slide, which was a lot more complicated, right? 1 over the square, not 1 over, sorry, x over the square root of 2 times x squared plus y squared. Not plus either. Y over the square root of 2 times x squared plus y squared. And then 1 over the square root of 2. And I have run out of space. I think I can move it a little bit. Let me see. No problem. And this is then times ds, which is the square root of 2 dA. We pretend that says dA at the end. No problem, right? All right. So let's actually do this dot product first, and then we'll get to our limits of integration, I promise. But let's do our dot product first. So when I do our dot product, when you do the dot product, when we do the dot product, what happens? The first one's 0, right? So I'll write it down. Of course, if you leave it off, it's fine. What about the second one? It's the same thing, right? Do you guys want to distribute the square root 2 1 through this while we do it? Are you good with that? It's actually really nice, right? Because when I distribute my square root of 2 through this, it cancels out the square root of 2 that's in the denominator in all the cases. Are you guys with me on that? So we could actually do that at the same time if you'd like. If you don't want to do it in a separate step, that's okay too. But this should be then y over x squared plus y squared under a radical. And then plus what? Y, yeah. 1 times y or y, yeah. Oops. And then I've got dA at the end. What do you think we might do next to get this? I mean, we're obviously going to have to find limits of integration. Do we want to leave it in xy, or do we want to change it to something different? What do you think? Yeah. So I hear two of you describing things that sounded like polar to me. Does it look like something that might be helpful to be done in polar to you? I think it probably does, for a couple of reasons. One, simply because you're having the x squared plus y squared, but also take a look back at the original problem. Do you see this piece right here? This tells me I'm inside of a what shape? A circle. And I know the limits of integration on that quite easily, don't I? Yeah, so that's going to be very convenient to work with. So let's take a look at this. All right, so let's go with changing this into polar. So let me just jot down as you were saying out loud. So x is going to be equal to r cosine theta. Y is r sine theta. And I think Taylor had told me the x squared plus the y squared would be the r squared, which is also convenient since we have that piece in there. Okay, so let's do the change of variables first, and then we'll do the limits of integration second. So the y is going to be r sine theta on top. This is going to be what in the denominator? It's just r. And then plus y sine theta. I'm sorry, r sine theta. That didn't look right. Thank you. R sine theta. And then we're going to have to do this with respect to dr and to d theta. Oh, I missed it. You're right. Thank you. We do need a factor of r. Thank you. All right, so what would my limits of integration on r be? 0 to 2. How about my limits of integration on theta? Yeah, 0 to 2 pi. Because we're working with the whole circle. Oh, wonderful things simplify, don't they? What happens? These r's cancel. That's nice. And so I have 0 to 2 pi, 0 to 2. You could do these in the opposite order. We tend to put the theta on the outside. It doesn't always matter. On this one, it doesn't matter specifically because we've got numbers everywhere. But And then I've got this r to distribute through from over here as well. So I've got r sine theta plus r squared sine theta, and then dr d theta. All right, so what's the antiderivative with respect to r? R squared over 2 sine theta plus and we're evaluating from 2 down to 0. So if I evaluate that 2 down to 0, what do I get? And those, I think, probably could be combined, right? You wouldn't have to. You could leave them separate, but could you combine them? Sure. What's 8 over 3 plus 2? 14 over 3. So we're almost done with this one. Last slide. So my integral from 0 to 2 pi, what do we say, 14 over 3 sine theta d theta. And I need the integral, excuse me, of the sine of theta, which is what? Negative cosine of theta, which we'll evaluate at 2 pi down to 0. So evaluated at 2 pi and evaluated at 0, what happens? What'd you say, Taylor?
She said it.
Oh, what'd you say, Tally? It's 1. All right, both of them are 1, right? They're the same. So let me put my negative 14 thirds out here. So when we evaluate that at 2 pi, we get 1. When we evaluate it at 0, we get 1. So we get the exact same thing when we're subtracting. So we get a big whopping 0 for our answer. Yes, we do. All that work for nothing. Literally, right? A 0 at the end. And of course, we wouldn't have to have 0. It just had to be the function we were working with. All right, so let me go back to the slide that had the homework on it so that you can write those down if you didn't last time. This is page 1042, 21, 24, 27, 34, 37, 38, and 41, 44, 45. Surface integral. So some of them you're going to actually be finding surface area on, I think, the first 3 maybe. And then the other 6, I believe, you're going to be finding, well, 3 of them you'll be finding surface integrals, and the other 3 are finding flux, which is related to surface integrals, of course.